Hi everyone, welcome back. In this section we're going to come back to parametrized curves or space curves, and we're going to look at how to compute arc length and curvature. So arc length is just the length along the path or the length along the curve. Curvature is about how it's bending in space. So let's do a quick reminder. We've already seen arc length before. We've seen it in Calculus 1 in the context of parametrized curves or parametric equations. So if we have a parametrized curve in the plane, so the x-coordinate is given by a function f of t, the y-coordinate is given by a function g of t, then the arc length is given by the integral of the square root of the sum of the squares of the derivatives. Now one thing we can do with this is we can recast this into vectors and vector functions, and I can notice that that square root of f prime squared plus g prime squared, that I can think of as the length of a vector function r prime of t. So where r prime of t is f prime of t, g prime of t. So in other words, I'm thinking of r of t as the vector function which has components f of t and g of t. So nothing new here other than just recasting an old formula that we've used and known in Calculus 1, but recasting it in the light of vector functions. And what this really says is, now if we think about it in this way, I've got if I think about a particle traveling along a path, and the path is given by this vector function r of t, then what r prime of t is it's essentially the velocity vector at any given point. When I take it to magnitude, that's essentially the speed. And so what this is saying is that the distance the particle is traveling is precisely the integral of the speed function. And that's something that we used quite a lot when we interpreted the derivative and integrals in terms of quantities in physics of distance, velocities, accelerations, etc. So that's a formula we've used before, we've introduced before, just cast in a new light. We can take this and we can extend it to parametrized curves or space curves in 3 dimensions. So if I have a curve given by the vector equation, r of t is given by f of t, g of t, and h of t, those 3 component functions, then the curve is traversed exactly once over a particular interval. Then we can compute the length of the curve by integrating, and I'll just focus on the very last result. We just integrate the magnitude of the derivative function. So it's a very nice formula for computing the length of a curve, so the arc length of a curve. So we can do an example of this. Let's find the length of of the arc of a circular helix with this vector equation, cos t, sine t, and t, from the point 1, 0, 0 to the point 1, 0, 2. So we're in a situation where we've got our helix. Maybe I'll draw it in blue. It's starting at the point 1, 0, 0, and it's ending at the point 1, 0, 2 pi. And what it's doing is it's going around, sort of like a spiraling staircase, circling around the z-axis and coming up to this new point, which is sitting directly above the point we started at. And we'd like to know what is the length of the curve that connects these 2 points. So from this we can take its derivative. Derivative of cos of t is negative sine of t, derivative of sine of t is cos t, derivative of t is 1. We can go ahead and compute its magnitude. That's given by sine squared of t plus cos squared of t plus 1, square root. Sine squared plus cos squared is 1, so that's a 1 plus a 1, or in other words, root 2. So there's our magnitude of our derivative. And now the arc length is going to be the integral as t goes from, well, we need to know the values of t. T is 0 when we start, and the value of t is 2 pi when we end. We can read those off as sort of the last components there, the last coordinate of the point, because that's given by t. So this says that we're going from 0 to 2 pi. The integral of the magnitude of r prime of t, so we'll write that in there, dt, and that's the integral from 0 to 2 pi of root 2 dt, or 2 pi root 2. And so that's the length of that curve. The length of this curve is 2 root 2 pi. All right, so that's an example of how we can compute the length of a space curve. Now, the rest of this section is really about what can we do with this? What can we do with this? Now that we know how to compute length, we can do things like introduce an arc length function. So that's a function that returns the length along a curve, which varies with the variable t that you'll sort of end at the point of the curve on. Once we do that, then we can introduce re-parametrizing curves in terms of a new parameter, one which the curve is traced out in constant speed or with constant speed. So in other words, we re-parametrize the curve so that in this case it's a helix, but the helix, at any given point along the helix, the particle is moving with a speed of root 2. What I would like to do is try to re-parametrize it if I can, so that at any point along the curve, the particle is moving at a speed of 1. A unit speed curve, in some sense we're thinking about, rather than just going around at root 2, speed of root 2. Most curves, the speed will vary because the derivative, in this case the magnitude of the derivative ended up being a constant, but it might not be. The magnitude of the derivative could vary, in which case the particle could be speeding up and slowing down and speeding up. And we'd like to re-parametrize the curve so that it's traveling at along a constant speed. The reason we'd want to do that is because then we can ask questions about how is the tangent vector changing. And I don't really want to be interested in whether the tangent vector is shrinking or elongating. In other words, the speed is changing. I'd like to know how is the tangent vector changing due to direction changes, not length changes. Because direction changes are going to pick up how the curve is curving in space. And it's not so dependent on how it's been parametrized. So whether it's traveling at twice the speed or 3 times the speed of a different parametrization, yet the same underlying curve is there. So that's kind of where we're going with this in this section. So the very first thing we're going to do is we're going to introduce the arc length function. So the arc length function, suppose C is a piecewise smooth curve given by a vector function. Oh, we got function written twice there. Get rid of one of those. R of t, which is got component functions f of t, g of t, h of t. And let's suppose C is traversed exactly once as t travels from A to B. We're going to define its arc length function as s of t, where we're taking the arc length from the point corresponding to t equals a out to an arbitrary t value. So the key thing to notice in this whole definition is right up there. That's a variable. Unlike in the definition of the arc length, it was a constant. It was b. So that would be the arc length along the curve from a specific point to another specific point. Here it's from a specific point to a variable. And so that variable t can change, in which case as t changes, the length of the curve we're interested in finding the length of, that's changing. So this is a function of t. So that's the only thing that's changed here. So we'll get a picture of this situation. We've got a curve in space. It's doing whatever it does. And the idea is there's some point we're taking as our frame of reference for measuring, in some sense, the length from. So we've got this t equals a, and I'm imagining this is the direction of increasing t. And I go out to another point for an arbitrary value of our parameter, call it t, so that thing's going to be variable, and I go ahead and I compute the arc length of this. And that arc length is given by s, but since it depends on where I'm stopping at, it's a function of t. And that's what this is capturing. The length from that point corresponding to t equals a out to an arbitrary point corresponding to the value of the parameter t is given by the integral of r prime of, and I switched the limit of integration to a dummy variable, variable of integration, which we just called u. I didn't want to use t again because t is already being used in the upper limit of integration, so we just switched to a dummy variable, r of u du. Okay, so that's what our arc length function is. It's a function that returns the length along the curve from that starting point t equals a to some arbitrary point. Now, using our fundamental theorem of calculus, we've got that, well, we can look at it right here. If I look at this equation, and I think, let's find the derivative of this function s. Well, the fundamental theorem of calculus says to find the derivative, you just take that upper limit of integration, which is the variable, and you pop it into the integrand. The lower limit of integration is a constant, so fundamental theorem of calculus says when you differentiate this thing, you get exactly what's in this box called fact. ds dt is just the magnitude of r prime of t. The nice thing about this expression is what this is two ways to describe the speed. So this is two expressions for speed. The one on the right is essentially the velocity, so it's the derivative of the position function, which is the velocity function, and you're taking its magnitude, and the magnitude of velocity is speed, so that's the interpretation of the thing on the right. It's speed, rate of change in position. What is on the left is the rate of change in position, ds dt, and that's also speed. So these are two interpretations for speed. So let's go ahead and do an example. Maybe I'll leave that up there for the time being. So what this example is we've got this helix, and I'll draw our helix out. So it looks something like this. We go around the vertical axes and so on, and we're just spiraling around. That's what our helix is. And we're asking to re-parametrize the helix with respect to arc length. So what does this even mean? Let's go to a quick demo. So I'm going to introduce a function, namely our vector valued function, r of t, and that's going to be our cos t, comma sine t, and t. So there's our function, and it says variable or function, just so that's our function. And now I want to plot a parametrized curve using that function. So when I click the parametrized curve button, it gives me basically the curve I wanted, but I don't want to plot it this way. I want to plot it by just telling it use that function that I defined above. So this is a very nice way of defining the function first and then plotting the curve later. Now here's the reason I wanted to do it this way, is because now I can put a point on it. And when I put a point on it, I can say r of 0, for example. And now it picks the point on the curve corresponding to the parameter 0. And then I could do r1, r2, r3. I could put in different t values and see where the point is. To get a whole bunch all at once, I can add a slider. and then that slider is called variables capital T, so I could put capital T in there, and then I could drag the slider around and it'll update the position of the point based on where the slider is. So that's why I did the construction in that way. I'll move the slider up so it's at the top of the page. Okay, so if I click the play button next to the slider, it says go at 1 times speed, so there's our point moving along our curve. And it just resets after it gets to 5 and it goes back. Alright, now this is where the story gets more interesting, because now I can do the same thing again, create a new function. I'll move this function down below just so the new construction is going on below. Here's our new function. It's going to be this vector function, which I'll call r2 of t. It's basically going to be my old function, but I'm going to put a 2 times in front of each of the t's. And I'll change, well, and then I'll plot it. So I've created the function. Now I'm going to plot the parametrized curve. And the curve I'm going to plot is the R2 curve. And you may see things got extended. You can see that it looks like it's overlapping with the previous one, and in fact it is. I will change the color. I will take that first one, that first parametrized curve, and I will give it a Z bias of 1. That means if it's overlapping with another object, show this one out front. Z bias means closer to the viewer's eye. So we can see that I've got 2 parametrized curves, or 2 parametrizations, I should say, but yet they define the exact same curve. They're both the helix. So what's really the difference? The difference is if I go ahead and put a point on the second one, so this is, let's call it point 2, I'll color it green, and I'll make it R2 of t. And so remember, the slider here is just a slider. It's just a variable t that's moving at some constant rate. And then we're seeing how the blue and the green points are being traced out. So what do we notice? We notice the green point is traveling much faster along the curve than the blue point. In fact, it's traveling twice as fast. Twice because of that extra 2 I've put in front of each of the t's here. So this is what's known as the same curve having 2 different parametrizations, where the second parametrization is twice the speed of the first parametrization. How would we actually detect these speeds? Well, we would construct the derivative and find its magnitude. When I construct the derivative of the R2, I would use the chain rule, and I get a 2 that comes out of every derivative, and then when I compute the magnitude of that derivative, the magnitude of this derivative would be twice the magnitude of this derivative, and that's the 2 times the speed. What is the speed of this curve? Well, we've already calculated that. We'll go back to our notes, and we'll see that the part we calculated already was right here. The magnitude of r prime of t is root 2. That means that blue point is traveling along the curve at a speed of root 2. I would like the particle to be traveling along the curve at a speed of 1, unit speed. So then the question is, how do we re-parametrize it so that it's unit speed? We can play around with it, right? If I put 3's in here, then this is 3 times as fast as the blue point. But I want it, the blue point is traveling at a speed of root 2. So I want it to be traveling at 1 over root 2 times as fast. So that means I can put in here square root of 2 and get rid of that 3 and put a square root of 2 under there as well, and get rid of this 3. and put a square root of 2 under there as well. And now we can see the green point is traveling slower than the blue one. And that's because the blue point is traveling at a speed of root 2, the green one is traveling at a speed of 1. And so we would call this parametrization here, this R2 parametrization, a unit speed parametrization of the helix. It's a re-parametrization of the helix, but in such a way that the point or the particle is traveling along at a speed of 1. So that is really what this question is asking. It's asking us to re-parametrize the helix with respect to the arc length. And that means, if we re-parametrize in terms of arc length, it means that for every unit change in our parameter, we want it to move 1 unit along the curve. That means we want it to have a speed of 1. So re-parametrizing in terms of arc length is really just a question about making sure it's traveling with a speed of 1. So let's see, how could we do this? Well, first we need to come up with the arc length. So we'll look at, well, okay, we've got r of t written up there, so I'll write down r prime of t. That is negative sine of t, cos of t, and 1. We've got the magnitude of r prime of t, which is the magnitude of that vector, which is root 2. That is ds dt. That's root 2. In other words, I'm just using that boxed formula above there, that the magnitude of r prime of t is precisely ds dt. So that means that if I integrate this, or take the antiderivative, then s is root 2 of t, because the derivative of s with respect to t is root 2. And now, from here, I can rewrite t, so it's s over root 2, and that means if I substitute s over root 2 for the variable t in our original function, then I'm going to get a new parametrization of the helix, but it's a unit speed parametrization. So re-parametrization in terms of s is going to be, we'll call it something else. I don't want to call it r, so I'll call it rho, because rho is the Greek letter of the alphabet sort of corresponding to r. So our re-parametrization is going to be rho of s. That I get by taking my current parametrization r, but replacing t with its expression in terms of s. So I'm thinking of it as t as a function of s. And so that's cos of, and this is where I plug the s over root 2, sine of s over root 2, and t, which becomes s over root 2. And that's precisely the parametrization we had in the construction, where we had root 2 dividing each of the parameters. And so there's our re-parametrization. And the key takeaway here, the key thing to note why we did this, is as follows. Because if I take the derivative of it, then what I get is, well, I'll do it a different way. If we take its derivative with respect to s, then we get these root 2's coming out front. So maybe I'll do it that way, first of all. So we take its derivative with respect to s. So what I'm going to get is, I get all of these 1 over root 2's in front of everything. And the derivative of cosine is negative sine s over root 2. So the idea was I take the derivative of cosine, I get a negative sine. The derivative of the inside, which is the s over root 2, is a 1 over root 2, so I've brought that out front. Take the derivative of the next one. The derivative of sine is the cosine of s over root 2. The derivative of the inside function is 1 over root 2, so I've just pulled that out front. And the derivative of the last one, which is s over root 2, just becomes 1 over root 2. So I bring that 1 over root 2 out front, and it just becomes this. And so now when I take the magnitude of it, I'll slap magnitude signs around this thing. That is 1 over root 2 times the magnitude of that vector, and that vector is root 2. because it's sine squared plus cos squared, which is 1, plus the other one, square rooted, so it's root 2, and so this is 1. So this is a unit speed parametrization, because I've got a parametrization, and I work out its tangent vector at every point, and its magnitude is always 1. Another way to think about this, so maybe I'll say alternate, is the following way. I'm going to go, what is the magnitude of p prime of s? Well, I look over here and I see it's a composition of two functions. So what is it? It's dr dt times dt ds. So that's the chain rule for that derivative. And again, I have magnitudes around it because I'm taking magnitudes of these things. And so this is r prime of t, that's what dr dt is, magnitude. And I got dt ds. Well, that's just the reciprocal of ds dt. Oh, but the top and the bottom are exactly the same quantity. So this is 1. And so that's another way to think about why this should be 1, using the chain rule. Okay, so the bottom line here is we can take a parametrized curve and we can re-parametrize it using the arc length parameter, so that now the particle, if we think about it as a particle's traveling along it with unit speed. Or in other words, the tangent vector at every point is always a constant 1. It's always a unit length tangent vector. So we've eliminated how the curve is changing, or how the tangent vector is changing along this curve. We've eliminated the fact that it's changing because of how fast it's moving. It's always unit length. The only thing that's changing with the vector now is the direction it's pointing in. And that's nice because that leads to our next concept of the rate of change in that tangent vector will give me an idea of how the curve is bending, because the rate of change in that tangent vector is all about the direction change. It's not about the length anymore, because I've always made it length 1. So that gives rise to this notion of curvature. The curvature of a curve is the magnitude of the change in the unit tangent vector with respect to arc length. So I've taken my vector, my tangent vector to the curve, which is parametrized by arc length, and that's going to be a unit tangent vector. And then we take its derivative, the derivative of that tangent vector. So how does that tangent vector change? That's dt ds. And how it's changing is really just how is its direction changing. And so dt ds is a measure of how the curve is bending. So that's why we're taking the magnitude of this and getting the curvature. So we got a numerical value that's telling us how the curve is bending. Now, in order to compute this, we'd have to do a bunch of steps. So you think about how we would compute this curvature value, this kappa. The first thing I'd have to do is I'd have to re-parametrize r in terms of the arc length, s. Once I've done that, so we've done an example of that back here. We've re-parametrized the helix in terms of arc length, and there was our re-parametrization. So now it's parametrized with the variable s, which was the arc length. So we'd have to re-parametrize it. And then in order to continue to compute the curvature, what I'd have to do is we'd have to find the unit tangent vector. So we'd have to take the derivative of this re-parametrization. Once we found that, then we'd have to take its derivative, t prime of s. And then once we've done that, then we'd have to take its magnitude, t prime of s magnitude. So those would be 4 steps we'd have to do, and none of them is very straightforward. Reparametrization can be difficult. The example we did with the helix was fairly straightforward because there was this linear relationship between s and t. But then we'd have to form find the tangent vector. That's taking a derivative. Then we'd have to take the derivative of that, and then we'd have to take the magnitude. So there's a lot of steps going on here. Can we get away with finding the curvature without having to do all these steps? And the answer is yes. And we'll do it in 2 stages. We'll see how we can eliminate having to do the reparametrization step as a first step, but then we'll also see how we can avoid having to even do the unit tangent vector step. Alright, so in this case, we want to show that the curvature, which is defined as the rate of change, or the magnitude of the rate of change in the tangent vector, the unit tangent vector, we're going to show that it's actually able to be computed by looking at the rate of change in the unit tangent vector in the original parameter, t, rather than in the new parameter of arc length, s, divided by r prime of t, the magnitude of that. So how do we do this? Well, first thing I do is say, in order to compute the curvature, I need to know dt ds. That's the definition up above. How do I compute that? Well, if all I have is that capital T, the unit tangent vector, is defined in terms of the parameter t, then I'd have to do a chain rule. dt dt, d little t, times d little t ds. So this is the chain rule. Okay, so it says, I want to take the derivative of t with respect to s. Well, it's defined in terms of little t. So let's do the derivative of it with respect to the intermediate variable little t, and then the derivative of little t with respect to little s. And then I can do a little bit of a rearrangement here. I can divide by the reciprocal of dt ds, which is ds dt. And then at this stage I can take magnitudes. So dt ds in magnitude is equal to the magnitude of dt dt all over the magnitude of ds dt. And what are these things? Well, the dt dt, the thing up top, is t prime of t, and that's a magnitude. What is ds dt? Well, that's the magnitude of r prime of t. And what is this thing over here? dt ds magnitude, that's the curvature, and so there's our formula. So there's a way we can compute curvature without having to go through a re-parametrization. And this is nice. So let's see how we can find the curvature of the helix using this technique. So in order to do this, we would need to first find the derivative. So that's negative sine t, cos t, 1. And then once I've found the derivative, then I need to know the magnitude of that, because that's a part of the formula that I'm going to be using above. So the magnitude of this is, as usual, it's the square root of 2. What else do I need to know? Well, I need to know the unit tangent vector. So the unit tangent vector is the tangent vector divided by its length. And so that's the tangent vector divided by root 2. So it's negative 1 over root 2 sine t, 1 over root 2 cos t, and 1 over root 2. Once I have that, then I need to know its derivative. And so that's going to be negative 1 over root 2 cos t, 1 over root 2 with a negative sine t, and 0. And then lastly, I'm going to need to know the magnitude of that. So the magnitude of t prime of t is the square root of, so maybe we can be a little bit more strategic in how we do this. There's this constant in front of each of these. And so this is really just negative 1 over root 2 times the vector cos t sine t, and that's a unit vector. So the length of this thing would be a 1 over root 2. So there's our length. And then finally we can go ahead and compute the curvature. The curvature is given by the magnitude of t prime of t over the magnitude of r prime of t. And we've got that that's a 1 over root 2 over a root 2, or a half. And so the curvature of the helix is a half. And you might say, well, what does that mean? Okay, I know what curvature means. It means it's bendy. But if it's a half, does that mean it's really bendy, or does that mean it's not bending so much? I don't really know what curvature means, and that's fine. I will give you a way to sort of think about this. So a circle of radius A has curvature 1 over A. So a circle of radius A has curvature 1 over A. So that means a circle that has a really big radius has a fairly small curvature. And you kind of think, if you zoom in and zoom in and zoom in on a little portion of a large circle, it doesn't bend very much. Whereas if you have a circle of a really small radius, let's say the radius is 1 over 10. So 1 over 10 is a really small radius circle, so it's really sharp in terms of how it's turning, then its curvature is 1 over 10, or 10. So 10 is the curvature of a circle of radius 1/10. 1 is the curvature of a circle of radius 1. A half is the curvature of a circle of radius 2. And so this gives you a feel that, okay, in this case, we got a curvature of a half, which means it's kind of curving like a circle of radius 2 would curve. And so that's how we can get a feel for what the curvature means. If you want to verify what's in this circle box, or this purple box, let's say you want to verify this. Well, we can. Right? I'm not just making up a statement here and just saying, here's a statement of fact. No, we can verify this. So how would we verify this? Well, you could, for example, take a curve which represents a circle of radius A. And so that would be A cos t, A sine t, and 0. And so that would be a circle in the xy plane with a radius of A. And then you could go through the calculation we just went through above for the helix, but in this case it would be a little bit more straightforward because instead of t being the z component, you've got 0. And you'll see that what comes out is the curvature is going to be 1 over A in this case. So we could verify this fact, but this is a nice, handy way to help you interpret what a value is that you get for curvature, what it actually means. So this means that this helix, as we spiral up, at any point this particle is sort of going around or bending around the corner. Or if you want to think of it, you're in a cart and you're going around a corner. How is it curving? How is your road curving? It's curving like as if it was a circle of radius 2 right at that point. All right. Now, you can still see that there was a bit to this in terms of our calculations. What did we have to do? Well, I started with r of t. I had to differentiate it. Then I had to normalize it. Then I had to differentiate the normalization of it. Then I had to normalize that. And then I had to take their ratio. A lot of calculations involved. One of them being a normalization. Can we avoid that? So from the definition, we've already avoided this step, number 1. We didn't have to re-parametrize. That's what this formula allowed us to do. Now can we get a new formula that doesn't even involve capital T, that doesn't involve a normalization happening? And the answer is yes, we can. There's an even more beautiful formula for curvature that doesn't involve normalizing anything, and it's given by this. I shouldn't say doesn't involve normalizing. Normalizing is just dividing by a length, and we are dividing by a length here, but it's not that we're normalizing and then trying to differentiate that. Like we didn't have to go with a capital T prime, for example, in this formula. So we can compute the curvature, and we can do it straight from the original parametrization. We just need 2 derivatives. So this tells us that the curvature is given by r prime of t cross r double prime of t divided by the length of r prime of t all cubed. We're going to prove this, and then we'll do a calculation using it. So let's go ahead and prove it. So how are we going to prove it? Well, we'll start off with this statement here. What is capital T? I'm going to drop the arguments here just to make it clean, more easily readable. So what is capital T? Capital T is r prime divided by the magnitude of r prime. So that's what the unit tangent vector is. Okay, so that means that we can write r prime as this scalar times capital T. But that r prime magnitude is just ds dt times capital T. And so that's actually a formula for us, at least in this stage, worth remembering, because what I can do with this is now I can differentiate star again, and I'll differentiate it with respect to t. Maybe I'll say with respect to the variable t. So when I differentiate it, I get an r double prime. And the other side, it's a product of two things. It's a ds dt, whatever that function is, times capital T. So I'd use the product rule here. And I'd get d squared s dt squared times t plus the first function times the derivative of the second with respect to t. So we get that. And now what can I do? Well, what I notice is that, again with star, star is a multiple of the vector capital T. In r double prime, it's some combination of the capital T vector and the dt, d little t vector. I'm going to just change this and write it as a t prime, just to make it a little bit more clean looking. And so r double prime is a linear combination of t and t double prime. And here's one key thing to recall. Recall t is perpendicular to t prime. And you may say, I don't recall that. When did we ever use that? And we'll go back to it and see. Right after we stated the differentiation rules for vector valued functions, we had this example number 12. And the example number 12 said, show that if we have a vector function that has constant length, that its tangent vector is orthogonal to its position vector. So in other words, its derivative and itself are perpendicular. And that's what we concluded here. And we got it by just knowing that if they were perpendicular, their dot product was a constant, and so we differentiate through and we get that the dot product of r prime and r had to be 0. That's what we're going to use right here. T is a vector function of constant length. It's always of length 1. And so when you differentiate it, you must get a vector that's perpendicular to itself, and that's t prime. So these two vectors are perpendicular to themselves. So what that means is I've decomposed r double prime into two vectors, one in one direction and one in a perpendicular direction. So kind of like this, a horizontal and a vertical direction, t and t prime. So what I can do with this is I can now take the cross product of r prime with r double prime. And the reason we're going to do that is because r prime is parallel to t. So when I take the cross product of the two, so I'm taking the cross product, if we look back, of this thing and this thing. That's what I'm taking the cross product of. So the first components, when I take the cross product, it's a vector in the direction of t cross a vector in the direction of t. So those are two vectors that are parallel. When I cross them, that's 0. So that's going to be a 0 there. Plus the cross product of the other two vectors. The scalar can come out front as a square, and then we get a t cross t prime. And so now I can take the magnitude of that and see what happens. When I take the magnitude, I get a ds dt all squared, so that comes out front. And I got the magnitude of t cross t prime. And so this is where I'm using this fact right there to go to the next step. Because if they are perpendicular to each other, then the magnitude of them, of the cross product, is the magnitude of each of the individual vectors times the sine of the angle between them. But there's a right angle between them, so the angle between them is pi by 2 or 90 degrees, so the sine of that would be 1. And so the magnitude of the cross product is just the multiplication of their two magnitudes. That's where I'm using that orthogonality. This is a unit vector, so that's 1. So this becomes ds dt squared d times the magnitude of t prime. And we're almost done, because at this stage we've just got that t prime in magnitude is equal to r prime cross r double prime in magnitude all over ds dt squared. That's r prime cross r double prime magnitude. ds dt, that's the magnitude of r prime. So that's r prime magnitude all squared. That's just the two expressions for speed. I'm just using the r prime expression. And lastly, if we look at our formula for curvature, the one we derived just above, this one here, this formula says that the curvature is t prime magnitude divided by r prime, the magnitude of it. So our curvature is given by the magnitude of t prime divided by the magnitude of r prime. The magnitude of t prime is written above in terms of the cross product, divided by r prime squared, but then we're dividing by an extra r prime magnitude, so there's our cube. And so there's our formula we wanted to derive. So that tells us that we can compute the curvature of a curve without having to worry about finding the normal, without having to worry about finding the unit tangent vector, or even without having to re-parametrize in terms of arc length. Let's go ahead and use this to compute a curvature. So in this case, we're going to need to know what r prime is. So this is 3, 4 cos t, negative 4 sine t. We're going to need to know the second derivative. That is 0, negative 4 sine t, negative 4 cos t. Then we're going to need to know the cross product, r prime, and it's important to get the order right in the cross product. Usually it's important, I should say. All that matters is if you get the order wrong, you just introduce an extra minus sign. But notice in the formula we're taking the magnitude of the top anyway, so that would strip off the minus sign. So normally it's important to get the order right, but in here it wouldn't be drastic if you got the order wrong. The answer would still come out the same. So we want to find the cross product. In this case, I'll just write down what it is. You can go ahead and verify by double checking, by doing the cross product. So it's negative 16, 12 cos t, negative 12 sine t. So then I'd want to know the magnitude of this. And the magnitude of this would be 16 squared plus 12 squared. And that ends up being 20. And so then the curvature at a particular point t along the curve is given by r prime of t cross r double prime of t all over r prime of t cubed. And so that would be 20 over an r prime of t. I guess we should work that, the magnitude of r prime of t. So that would be the square root of 9 plus 16, so 5. And so that's 20 over 5 cubed, or 4 over 25. So that's the curvature of this curve. At any given point, it turns out it's of constant curvature. The curvature is independent of the point you're at. It's always 4 over 25. And if you want to make sense of that number, 4 over 25, 1 over that is 25 over 4, and that would be the radius of the circle that this curve is sort of curving like. It's curving like a circle. It's got like a bend in it at any point. It's bending or it's curving like a circle of radius 25 over 4 would. All right, so that's it for the main examples here. The next two examples are really just a throwback to Calculus 1, and taking these ideas and applying them. So normally we build things up and we say, here's an idea, let's go to the next dimension and so on. But these next two examples are really taking these ideas and just saying, let's see what they tell us in one dimension lower. So we can go ahead and we can produce curvature formulas that you may or may not have seen from Calculus 1. So a function, y equals f of x, we could talk about the curvature of that function, and it turns out to be given by this expression here. So I'm going to leave that for just a separate, shorter video where I do the curvature and verify this formula for plane curves, and then do an example of a plane curve finding a place of maximum curvature. So I'll do that in the second part of this video. We have finished the main content for three-dimensional calculus. This would just be a throwback to Calculus 1. Alright, thanks for watching. See you again next time.